Hey everybody, back here for factor analysis 4, confirmatory factor analysis, and introduction to structural equation modeling. The last of 4 videos in this 4-video series. Confirmatory factor analysis. What is confirmatory factor analysis? Well, let's contrast this to what we've been talking about in the first 3 videos, which has been exploratory factor analysis. Exploratory factor analysis addresses questions such as what factors underlie the data. With confirmatory factor analysis, we ask whether our data fit a specific factor structure. That is, we say, this is what we think is going to happen, and then we test that against the data that we actually have. So we're testing ideas about the structure of the data, in particular about the underlying factor structure. The factors that we've been dealing with are technically built as what are called latent variables. In contrast, we have measured variables. Those are the actual scale items. The latent variables are the unobserved constructs that underlie the data. We don't measure the constructs that we saw. For example, in the last video, we saw that we had a factor that represented kind of short memory items for letters and suffixes and things. The construct there is short letter memory, short letter skills, but we're not actually measuring short letter skills directly. We're measuring it through those 3 different tests that address short letter pieces. Think of the latent variable as the concept that's being measured, the concept that is related to those multiple items. All right, we'll take a little dip into the Big 5 personality inventory again. For example, within the Big 5 inventory, so here's some questions. I don't mind being the center of attention. I like to talk to a lot of different people at parties. I start conversations. I am the life of the party. These are questions from the scale, or what we would call measured variables. But one thing we can see with those items is that they all reflect something pretty similar. If you think about the sort of person who would endorse these sorts of things, somebody who's very outgoing, very energetic, loves to talk to people, they all reflect something very similar. And the items do fall together on a factor that the researchers term extroversion, one of the 5 Big 5 personality inventory factors. Now note that extroversion itself is not directly measured, but what it drives it is a response to these items that are all tapping a similar construct. People who are extroverts will tend to agree with these items. People who are introverts will tend not to agree with these items. Extroversion would therefore be the latent variable, whereas the individual questions that were actually asked, like I don't mind being at the center of attention, represent measured variables. Another example here, we'll take a look at the Wechsler Intelligence Scale for Children, or the WISC. The WISC includes a number of tests, and this is from one version of the WISC. There's lots of different versions of it. If you've taken a testing course, you maybe have some different items. WISC includes a number of tests. The ones that we'll take a look at are information, which is general knowledge, comprehension, math, similarities, vocabulary, digit span, which is ability to measure a string of values, and then picture completion, picture arrangement, block design, object assembly, and coding. Again, this is for children, so block design, object assembly, you're actually putting stuff together. This scale is broadly designed to measure 2 aspects of intelligence: verbal intelligence and performance intelligence. The items in italics are hypothesized to represent verbal intelligence, and the items in bold are thought to represent performance intelligence. So what we're going to do with confirmatory factor analysis is we're going to take these different measures, and we're going to see if they actually comprise 2 distinct factors. Unlike exploratory factor analysis, we're not going to let the computer derive what the factors are. We're going to tell the computer these are the factors and these are the variables that go with them, and we're going to get a number of statistics that address how well that actually fits the real data that we have. All right, the data file that we're going to look at is is available through the file whisk.sem.csv. It contains 12 intelligence measures, the ones that I just mentioned. Then we're going to ask whether the measures fit the proposed structure. We're going to build a model that reflects our latent variables, not out latent variables. I'll correct that when I get a chance. This looks largely like a regression equation, but we're actually predicting each individual measure from a latent variable that's supposed to be part of. We're going to see a bunch of new statistics that assess what's called model fit. That is how well the data actually reflect the structure that we proposed for it. And we'll also examine how well each of the measured variables can be explained by the latent variable. These are basically factor loadings. So we're going to use lavaan, which we've seen before in dealing with missing data and other issues. And we will see again when we talk about mediation later in the semester. We'll use lavaan, and first we'll read in the data. I've just called the data whisk. And you'll see the command CFA model. What we do with lavaan is we build a model structure, and then we feed that into a command. So the two things that we need here, verbal IQ, equal sign tilde, is equal to info, comp, arithmetic, similarities, vocabulary, and digit span. What this command structure is, anytime you see an equal sign and then a tilde, that is saying the thing on the left is the latent variable, the thing on the right, the things on the right are the measured variables, the variables that actually exist in your data file that are proposed to go with that. So you can see I built that for verbal IQ and for performance IQ. Only things here, stuff on the left, you can name it whatever you want. Stuff on the right has to match the names in the data file exactly. So that is built here. One thing to note, if you're getting errors, you're not going to get them on this command. This is just putting words into that thing called CFA model that gets fed into the command that we see next. So where you will get errors would be on this next step. I'm going to call my analysis fit. You can call it whatever you want. The command is CFA for a confirmatory factor analysis. I feed it the model, CFA model. I tell it what the name of the data is. And then I have this mimic M+. You can have this mimic other commercial software programs. This was just the last commercial software program that I used, and I kind of like the way it reports things. And then finally, we summarize our fit. And a couple pieces I like to add. Fit measures equal true. That's going to give us a number of different ways to evaluate whether our data fit this model that we proposed for it. And then standardized equals true basically gives you standard regression coefficients as your loadings. Here's the output, and there's a lot of output here. So I'll talk a good bit about what we need to look at and what we need to ignore. It can be really overwhelming because there's so much stuff. The biggest thing to look for here on this first part of the output is one major measure of fit, and that's the it's a chi-square test. Technically, it doesn't say that, but it's under model test user model. Test statistic is 70.6. Degrees of freedom is 43, and the p-value is 0.005. What that is addressing is whether your model deviates, or I'm sorry, whether your data deviate from the proposed model. Here, rejecting the null hypothesis would mean that your model doesn't fit. Failing to reject the null hypothesis would mean that your model does fit to the data well. So here we see, oh, well, we reject the null hypothesis that the model, and it tells us the model doesn't actually fit to our data. I would caution interpreting this too strongly, though. In general, most models don't fit based on the chi-square test. Some people have suggested a chi-square to degrees of freedom ratio of less than 2 as being a reasonable fit, and we see we would meet that because 70.6 over 4 is something less than 2. Some people sometimes confuse this with the model test baseline model. That baseline model piece, and that is testing a factor structure where nothing goes together. This is testing a nothing model. One thing you can look at is whether we've improved in explaining the data over the baseline model, although that's a really weak criteria. Pretty much always you would be improving over the baseline model, so not much to look at there. Usually people will report, however, this test statistic and its degrees of freedom as a way to compare between different models. And we'll see that sometimes we modify these models to look at changes, what doing certain things does to improve or make the model worse. Part two, way more models of fit here. I'll move myself down here so I'm out of the way. In general, we have a bunch of measures that are pretty commonly presented. CFI, Comparative Fit Index, is a very popular one. There's a lot of variance on that. Tucker-Lewis Index, somewhat less popular. For both of those, most sources would say 0.95 or higher would be a good value that would indicate good fit. We can see we're getting there on that. AIC and BIC, these are measures that are popular, but they're only really useful comparatively for comparing improvement from one model to the next. So for our first model, they're not really useful. The RMSEA, that is another good value. People will generally want the confidence interval for that statistic to fall entirely below 0.05. This is one of the most favored fit statistics around. I would definitely, if I were reporting values, I would report that chi-square value, the CFI, and the RMSEA, which people often call the RMSE. So I would report those three. We can see the RMSE doesn't really meet that criteria of being entirely below 0.05. It's a relatively stringent criteria, but it's a pretty good one. And then the SRMR, Standardized Root Mean Square Residual. It's a similar statistic to the RMSE. You want it to be low. Less than 0.05 is pretty good. I generally wouldn't present this if I had the RMSE as it's a favored statistic. You'll see that there's really no consistency, though, in terms of what people present. Just about everybody will present chi-square and a CFI or some variant of that, and the RMSE, but people present all kinds of different statistics. There's a whole bunch of other fit statistics that we can use that exist as well as these, but they all should basically be saying roughly the same thing. All of these tell us, we're not quite there yet. We don't have a great model fit. Now, in context, though, anything above 0.9 for the CFI is not bad. It's just not, meeting that criteria for good fit. All right. The next thing that we see are our loadings. These are basically like regression weights. Getting at the relationship between each of these individual variables and the latent construct, or technically how well each variable is predicted by that latent factor. A couple of things to observe here for verbal IQ. All of the variables we expected to go with verbal IQ are statistically significant. That is, they're at least related to that. This is a z-test that we get in this case. Notice for the first variable in each, information and pick completion, the estimate is simply set at 1. This is a technical aspect of how we do structure, how we do anything with latent variables. That first variable serves kind of as a basis for estimating the others. So you can change which one is fixed to 1 as a default. There's always got to be something that is fixed to 1. Looking at performance IQ, we see everything is significant except for coding. And that tells us that coding is not particularly well explained by this latent factor of performance IQ. It's not really related to it. This would be the same as having a very, very small factor loading if we were talking about exploratory factor analysis. Looking at this, we get a significance test that says, hey, this isn't related. And that's a useful thing to know because it tells us, hey, maybe coding isn't part of this factor. Maybe coding is its own thing. Maybe it belongs with verbal. Maybe we should just throw it out because it's not really measuring anything. Other stuff that we get here, we get the covariances. These are the covariances between the two factors. The value STD all is actually just the correlation between those two factors, and we can see that our factors are correlated. I didn't have to do anything to get the factors to correlate. That is a default in lavaan. So lavaan, again, is assuming that we're using factors that are oblique. Most of the good software packages now have that as the default, whereas the default used to be orthogonal. So you can see that the thinking on orthogonal versus oblique is changing a little bit. Then we get a lot of stuff that we can ignore. The intercepts here, we don't really have much useful information here, so we can just ignore all of those. Part 5, the output, you can see we get what are called the variances, what are listed as the variances. That value STD all is in this case, is 1 minus r squared. It's an index of explanation of the variable. So for example, for information, it's STD all is 0.423. If we subtract that from 1, it's 0.577, which gives us, it tells us 57. We are explaining 57.7% of the variability in information. That R square value, that's basically a communality, like we saw with exploratory factor analysis. If we look down to coding, one thing that pops out is that coding stinks. It's got STD all of 0.995. So if we take 1 from that, we were explaining about 0.5% of the variance in coding. So coding not well explained at all. There's the 2 factors are down at the bottom. You can ignore those 2. That really doesn't tell us anything. It's just included for consistency. All right, just to summarize the first confirmatory model, the fit was relatively mediocre. The CFI was 0.94. I should say that's a misprint there that I'll fix in your regular PowerPoint slides. The RIMSI was not great. It didn't have a confidence interval going down below 0.005. The AIC I'm presenting just for comparison for later, and then we saw the coding didn't fit on the proposed factor. So on the next example, you often see these models represented graphically like this. There's a lot of numbers here, but a few things to note here. The numbers on the left are the STD all, how much variance isn't explained for each of the individual variables. Then in the middle, where we see the arrows going from verbal IQ to these boxes. One thing to note here about this, latent variables are always represented with circles. The measured variables are always represented with squares, or in this case, rectangles. And that's just by convention. Also note here, it's verbal IQ predicting information, verbal IQ predicting comprehension. That's what those arrows are telling us. One thing is predicting another. What we see with those multiple arrows are the coefficients, and these are the standardized coefficients for the model. One thing I don't like is that they have NS down there for performance IQ going to coding. I'd rather see the actual value, but it's fine, we know that it's a small value. And then the number going between the 2 latent variables, this double-headed arrow, those indicate correlations, and that's the correlation between the factor. So that's what a typical model might look like. You've got the latent variable in the circle. You see what variables are related to it and how they load, and then you can see how correlated the 2 factors are as well. All right, I modified this model by removing coding, just so that we could have another example to look at and see how removing that bad variable might improve our fit. And you can see, one, our CFA value went up to 0.954. So now we hit that criteria on the not the CFA, the comparative fit index, the CFI. Tucker-Lewis index still not there. AIC, the fit on that, we'll have to compare that to the previous values, and then you can see the root mean square error of approximation, or the RMSE, is reduced a little bit, but the confidence interval is not improved by removing coding very much. And then just comparing the two, you can see CFA went up, RMSE confidence interval, well, it got a little bit wider, it went down a bit. The AIC, you can see that the AIC decreased by about 870 points. That's suggesting that the model did get a little bit better once we tossed out coding. The chi-square value, I may not have, yeah, I did include it here. The chi-square value is getting toward being non-significant. It's still significant at the 0.05 level, though. But we can see that that's improved. The ratio of chi-square to degrees of freedom will have also improved. So in example 2, I'd say, you know, the fit improved. It got better. Maybe not great model fit yet, but you can see how removing that variable that wasn't performing very well helped us out. Just as another piece to take a quick look at, lavaan defaults to using correlated factors, but I thought we could take a look and see what happens if we force the factors to be uncorrelated. It's the exact same code, except I add a line here, verbal IQ, tilde, tilde. Tilde, tilde is represents correlations between variables. And then I put 0 times performance IQ. What that does is it sets the correlation between those two variables, between those two latent variables, as 0, meaning that it would be now orthogonal factors. And just looking at some of the fit statistics, in terms of the test statistic and degrees of freedom, we can see that now the ratio is well above 2 to 1. The CFI has gotten worse. The TLI has gotten worse. The RMSE has gotten worse. What that's telling us is that when we remove that piece that proposes that the factors are correlated and we force them to be uncorrelated, the model no longer fits the data well at all. We can see we're now getting much worse model fit because we remove that piece. All right, confirmatory factor analysis. There's an example you can work through in your in the R file that has the other stuff with. I would just call that optional, since we're not doing a ton of work with CFA, but if you want to play around with it, there is an extra example in there for you. The last piece in this in this mini lecture is going to be talking a little bit about structural equation modeling. Just an introduction to structural equation modeling. What's really exciting about teaching in R instead of SPSS is that I can include stuff like confirmatory factor analysis and structural equation modeling. These used to be things that you would very rarely be able to teach unless you were at a university that had some high-priced software such as EQS or M+, or a whole host of other packages, other expensive software programs that don't have enough widespread use for a campus to purchase licenses. Structural equation modeling is a simple extension of CFA, and I say simple amusingly because it's not particularly simple, but we'll see that a lot of the concepts that we talk about in CFA relate directly to structural equation modeling. In fact, if you take a structural equation modeling course, it starts with confirmatory factor analysis generally. So we still have factors. We still have the same piece where we have factors and we have measured variables that are related to the factor. However, what we now have are factors that are going to be predicting each other, or you can have factors that predict a single measured variable, but we'll just take a look at factors predicting one another. I'm using some data from some of my studies. We have 2 factors related to contact, both positive aspects of intergroup contact and negative aspects of intergroup contact. Both are measured with 3 individual variables. So there's 3 measures for, that get at aspects of positive contact, aspects of negative contact. So those are 2 of my factors. And then I'm going to have 2 variables or 2 latent variables that represent stereotypes and negative attitudes. So these are 2 separate outcome variables. Each of those are also measured with 3 variables, 3 stereotype variables, 3 negative attitude variables. We're going to test a model where positive contact relates to less prejudice on both of those factors, but negative contact relates to more prejudice on both of those factors. And here is the example. You can see I've built my 4 latent variables. I have positive contact, negative at, and stereo. So I've built those from the 3 measured variables that represent each of them. And then I'm going to predict negative attitudes and stereotyping from both positive contact and negative contact. Notice here, this is probably the first example we've seen where we have multiple dependent variables in the same analysis, or what we would call a true multivariate design. Under correlations, I'm correlating positive contact and negative contact. You only have to correlate the predictor variables. Outcome variables, the things that are being predicted in the regression, are automatically correlated or correlated by default, and we would have to uncorrelate them, much like we did with the orthogonal factors that we tested in that third example. Latent variables are structured as before, and we're going to force positive and negative contact to correlate, and we're going to test a model, and we're going to see whether this fits, whether a model where we're predicting these prejudices from both positive and negative contact explains our data. And also we're going to get tests for each of these different predictions. We're going to see whether positive contact relates to more or less negative attitudes, whether negative contact increases stereotyping, for example. Here are the fit statistics. Oops, I don't want my head any bigger. Here are the fit statistics we have. We can see the chi-square test produces a pretty large result that is even above that 2-to-1 criteria. However, if we look at the CFI and the TLI, we get some pretty good fit values. The RIMSI is not is still not below that 0.05 criteria for the confidence interval, but it's a pretty good fit. And then SMR is relatively low as well. In terms of the output here, in terms of the measurement model, this is just whether each of the variables goes with the predicted factor. You can see they're all significant, and that's really the only thing we need to check out there. Okay, turning to the path coefficients, this is getting at whether each of the measures of prejudice, the dependent variables, are related to each of the contact measures. We can see that negative attitudes related to positive contact, and related to positive contact, positively related, the way that that's measured, the way that these variables are coded, that means more positive contact was related to fewer negative attitude endorsements. And then negative contact is negatively related, meaning that it is related in such a way that more negative contact has lower scores on this attitude scale, where lower values indicate more negative attitudes. So positive contact related to better attitudes, negative contact to worse. Stereotypes, in the way this variable was coded, higher values for stereotyping indicated more strongly endorsing stereotypes about other groups. Here we see positive contact related to less stereotyping, negative contact related to more stereotyping, and we can see that these relationships are, of course, significant. We see correlations between the contact measures and the dependent measures. The contact measures were actually uncorrelated, and that's actually a pretty common finding in the literature, is that positive contact experiences and negative contact experiences are unrelated to one another. The quality of your contact and negative experiences with outgroups are not really related. Two separate ideas here, and that is addressed there. And then negative attitudes and stereotyping, the variables that get automatically correlated because they're outcome variables. So we can see that those were, as might be expected, correlated with each other. Graphing for structural equation modeling, there's not great tools for it right now. This is from a package called lavaan plot, and it's not ideal, but you can see what I would prefer to see is that the measured variables were up above positive contact and negative contact, and then we just could see one arrow each going from positive contact to negative attitudes and stereotyping and so on. Not a very well organized graph. I can probably mess with this a bit to get a better graph, but not a great graphing technique. But what we're seeing is each of the variables predicted, seeing the latent variables predicting each other. So positive contact has arrows that go to negative attitudes and stereotyping. Negative contact has arrows that go to negative attitudes and stereotyping. Also, each of the latent variables has arrows that go to the measured variables that they're constructed from. So you can see all of that here. The graph is, again, not ideal, a little bit confusing. You will see graphs of this nature in lots of articles, and well, usually the graphs are a little bit better. But this is a tool that you can use to get at least a quick visualization of these different pieces. I thought that lavaan plot wasn't very good until I played around with some other packages. Here's SEM paths. So definitely you can see that it does get worse with different packages. If anybody in the class can find a package to do good structural equation modeling graphing, I would definitely be interested in that. Certainly might be a great topic for an end of semester graduate student presentation. All right, with that, I think I am done with factor analysis. I will put up some slides on logistic regression, hopefully next week. But until then, stay well, wash your hands, stay inside,